welcome to the deep dive. Today, we're tackling something we all feel but maybe don't fully grasp. Heat.
Exactly.
We've got some great educational materials here, really breaking down the basics of heat, temperature, and what they do to stuff around us. And our mission, really, is to pull out the key ideas, maybe find some surprising connections, and just show why this matters without getting bogged down in super complex science.
Right, because heat is it's everywhere, isn't it? The sun, your coffee cup, it's constant.
Yeah.
But digging into what's happening, well, that gives you a whole new perspective. These sources give us a solid base, and we're here to kind of connect the dots.
Okay, let's jump right in then. What is heat? I mean, we know hot, we know cold. That feeling.
That feeling is key. It points straight to what heat is.
Yeah.
Energy. Moving.
Moving.
Yeah, energy in transit. It happens because there's a difference in temperature. Simple as that.
So if I touch, a hot mug.
Energy flows from the hotter mug to your cooler hand. Touch an ice cube.
Energy flows from my hand to the ice.
Exactly. Always from higher temperature to lower. It's a fundamental direction.
Got it. It's like energy trying to spread out, find a balance, and the material mentioned rubbing your hands together. You feel warmth, but there's no fire or anything.
Perfect example. That's mechanical energy, the motion, converting directly into thermal energy through friction.
Friction. Right.
It really shows heat isn't some sort of substance, it's a form of energy. The sources even mention James Joule. His work was crucial in proving this link between motion, kinetic energy, and heat.
So it's not just sitting there. It's energy doing something.
Precisely. And even simple actions can demonstrate this fundamental principle.
And this is where it gets really cool, I think. Because it's not just friction, is it? The sources talk about loads of ways energy transforms involving heat.
Oh, absolutely. Think about a burning candle. That's stored chemical energy in the wax, turning into light and heat.
Okay.
Or an old-style incandescent light bulb. Electrical energy becomes light, sure, but also a lot of heat.
Yeah, those get really hot.
Then flip it. Heat up some iron until it glows red or white. That's heat energy turning into light energy.
Right.
Or think bigger. A steam engine. Heat boils water, creates steam, and that pushes pistons. Heat converts to mechanical work.
Wow.
And even generating electricity in many power plants, burning fuel creates heat, makes steam, spins turbines. Heat ultimately becomes electricity. It's this constant conversion process.
Okay, so heat is energy moving, temperature differences drive it, and it pops up in all these energy changes. Where does it come from, though?
The main sources mentioned are fire, the sun, and electricity. Let's start with fire. Humans and fire go way back, obviously.
Way, way back. I mean, the sources remind us, discovering fire in the Stone Age, that was huge. Protection, warmth, cooking, even making better tools. A complete game changer for humanity.
And still vital, right? Cooking with wood or kerosene or natural gas. Cars run on burning petrol or diesel. Big power stations burn fuel too.
And the sources make this distinction, which is important, between things that catch fire easily and things that don't.
Inflammable versus non-flammable. Right. Petrol, LPG gas, lots of plastics, synthetic fabrics, even dry grass or paper. They have low ignition points. They burn readily. We call those inflammable.
Okay.
Then you have things like water, sand, pretty obviously non-flammable. They resist burning.
And knowing that difference is crucial for safety.
Absolutely. And the sources give some really practical safety tips, like don't wear synthetic clothes near an open flame, they melt, which is nasty.
Ooh, yeah. A good point.
Check for gas leaks, obviously. Keep flammable stuff, aerosols, paper away from heaters or electrical gadgets that might spark. And if someone does get burned...
Use water, cool water.
Exactly. Water is great because it can absorb a lot of heat energy without its own temperature shooting up too fast. That helps cool the burn and stop further damage. It has a high specific heat capacity, is the technical term.
Okay, next big source. The sun.
Yeah.
Can't really overstate its importance, can we?
Not at all. It's the main natural heat source for Earth, period. Life as we know it wouldn't exist without it.
It's not just warmth, though. It drives the weather, right? The water cycle.
Totally. The sun's heat evaporates water from oceans and lakes. It rises, cools, condenses into clouds, and then falls as rain or snow. That whole cycle is sun-powered.
And plants need it, too. Photosynthesis.
Essential. Plants use sunlight, water, and carbon dioxide to make their own food and release the oxygen we breathe. The sun's energy fuels basically the entire food web.
Wow. Okay, so sun, massive natural source. Then there's electricity. Not a source like the sun, but a way to make heat.
Exactly. It's more like a convenient energy carrier that we can easily convert into heat when and where we need it.
Like room heaters, electric kettles, or geysers for hot water?
Microwave ovens, toasters, electric stoves, loads of everyday things rely on electricity producing heat. Very versatile.
Okay, now here's something that kind of tripped me up a bit. The sources mention Sir Humphrey Davy rubbing ice.
Ah, yes. That's a brilliant experiment back in the late 1700s. We usually think heat hot things.
Right.
But Davy rubbed 2 blocks of ice together inside a vacuum chamber so no heat could get in from outside. And the ice melted.
Even though it was ice. Cold.
Yes. It showed that the mechanical action, the rubbing, was generating heat, enough to melt the ice. It proved heat is related to the motion of the particles within the substance, even in cold things. As long as they're above absolute zero anyway.
Absolute zero. That's like the coldest possible temperature, minus 273 point something Celsius.
Minus 273.16 degrees C, yeah. At that point, theoretically, all particle motion stops. But anything warmer than that, even ice, has particles jiggling around, and that motion is thermal energy. So rubbing them makes them jiggle more, generating heat.
Okay, that is a bit mind-bending. Even cold things have some heat energy because their particles are moving just less.
Pretty much, yeah. Which brings us nicely to temperature. It's related to heat, obviously, but it's not the same thing.
Right, what's the difference then?
Temperature is more like a measure of the intensity of that particle motion. It tells you the average kinetic energy, the energy of movement of the atoms and molecules inside something.
So high temperature means particles are zooming around like crazy.
Exactly, lots of kinetic energy. Low temperature means they're moving much more sluggishly. Less kinetic energy.
Okay, so heat is the energy transfer. Temperature is the measure of the energy level inside.
That's a great way to put it, yeah. Simplest definition. Temperature is just the degree of hotness or coldness.
And the sources mention something called the principle of calorimetry. Sounds important.
It is. It basically says if you put a hot object and a cold object together and they're isolated from everything else.
Like the hot milk and cold water example.
Perfect. The heat energy that the hot milk loses is exactly equal to the heat energy that the cold water gains.
Oh.
And this transfer continues until they both reach the same temperature. That's called thermal equilibrium. Energy is conserved. It just moves from one place to another until things balance out.
Makes sense, like pouring water between 2 buckets until the levels are equal.
Good analogy. Now, about measuring that hotness or coldness, our sense of touch isn't always reliable, is it? Remember that activity with the 3 bowls?
Oh yeah. 1 bowl, ice cold, 1 warm, 1 lukewarm in the middle. Put 1 hand in cold, 1 in warm, then both into the lukewarm one.
And what happens?
The hand from the cold water feels the lukewarm water as warm, and the hand from the warm water feels it as cold, even though it's the same water.
Exactly. It shows how relative our perception is. What feels hot or cold depends on what we just touched. Touch is subjective. That's why we need objective tools.
Thermometers.
Thermometers, right. The most common kind, the liquid and glass one, works on thermal expansion.
Things get bigger when they heat up, smaller when they cool down.
Precisely. The liquid inside, usually mercury or alcohol, expands up a narrow tube when it gets warmer and contracts back down when it cools. We just read the level against a marked scale.
The sources listed qualities for a good thermometer. Thin glass bowl, narrow tube.
Yeah. Thin bulb lets heat transfer quickly so it reads the temperature fast. Narrow tube, or bore, magnifies the expansion, so small temperature changes are easier to see.
Makes sense. And the liquid needs to expand uniformly, right? Not like expand loads at low temps and barely at all at high temps.
Uniform expansion is key for a linear, reliable scale. Plus, you want a liquid that stays liquid over a wide range of temperatures, doesn't freeze too easily or boil too readily, and it helps if it's easy to see and doesn't stick to the glass.
Okay, so mercury versus alcohol. Mercury's good because...
Doesn't stick to glass, it's opaque and shiny, so easy to see, expands very uniformly, works over a pretty wide range, freezes at -39 degrees, boils way up at 357 degrees C. It's a good all-rounder.
But alcohol?
Alcohol's big advantage is its freezing point, much lower than mercury, down around -139 degrees C for some types. So great for really cold places. It also expands more than mercury for the same temperature change, which can make it easier to read fine divisions.
But it boils much lower, right? Around 78 degrees C. So not good for high temps.
Exactly. That's its limitation. And you usually need to add dye to alcohol because it's clear. Water, by the way, is generally terrible for thermometers.
Why is that? Seems obvious.
Well, it sticks to glass, it's transparent, it evaporates easily, it doesn't expand uniformly, especially weird behavior near freezing. And its useful range is only 0 degrees C to 100 degrees C. Plus, it takes quite a bit of heat to change its temperature. Just not practical.
Huh. Never thought about why water wouldn't work. Okay, so how do they actually make a mercury thermometer? That sounds fiddly.
It is quite a process. 3 main stages. Construct the glass part, mark the fixed points, then calibrate the scale.
Construction means making the bulb and the stem with that tiny capillary tube inside.
Right. Then filling it is tricky. You heat the bulb, often in an oil bath, drive out the air, dip the open end in mercury, and as it cools, mercury gets drawn in. Repeat until it's full, get rid of any air bubbles, then heat it again to fill the whole stem and seal the top end.
Wow, okay. Then the fixed points. That's the 0 and 100 degrees.
For Celsius, yes. The lower fixed point, 0 degrees C, you get by putting the bulb in a constantly stirred mixture of pure melting ice and water.
Yeah.
You wait till the mercury level is steady, then mark it.
And the upper one, 100 degrees C.
That's done using steam from pure water boiling at standard atmospheric pressure. You put the bulb in the steam, not the boiling water itself, wait till the level is steady, and mark that point. Using a special apparatus called a hypsometer helps ensure the conditions are right.
Okay, so you have the 0 mark and the 100 mark. Then calibration.
Just divide the distance between those 2 marks on the stem into 100 equal parts. Each part represents 1 degree Celsius. You can extend the scale above 100 and below 0 too.
And reading it just makes sure your eye is level with the top of the mercury.
Yep, avoids parallax error. Looking at it from an angle can make it seem higher or lower than it is.
Right, so Celsius scale, 0 to 100 for water freezing boiling. It's pretty standard.
Yeah.
But there's Fahrenheit too.
Still used quite a bit, especially in the US. On the Fahrenheit scale, water freezes at 32 degrees Arium and boils at 212 degrees Arum.
That's a weird range. Why 32 and 212?
Historical reasons, based on different reference points initially. The key thing is there are 180 degrees between freezing and boiling on the Fahrenheit scale, compared to 100 on the Celsius scale.
Ah, so the degrees are smaller in Fahrenheit.
Exactly. And then there's Kelvin. That's the one scientists often use.
The SI unit, the sources called it.
Right, the standard international unit. The Kelvin scale uses the same size degrees as Celsius, but it starts at absolute 0. So 0 Kelvin is absolute 0.
Which is negative 273.15 degrees C. So to get Kelvin from Celsius, you just add 273, rounding it usually.
Pretty much. 0 degrees C is 273 K, 100 degrees C is 373 K. No degree symbol used with Kelvin, just K.
And those conversion formulas. Celsius to Fahrenheit is C divided by 5 equals F minus 32 divided by 9.
That's the one. C5 equals F32 9. Works both ways. Just rearrange it to solve for C or F.
Like 0 degrees C is 32 degrees Arf, 100 degrees C is 212 degrees Fahrenheit, and normal body temp, 98.6 degrees Arf, that works out to 37 degrees C.
Cool. So understanding those scales and how to switch between them is pretty useful.
Definitely helps when you encounter temperatures given in different units. Okay, deep breath. We've covered what heat and temperature are, the sources, how we measure temp. Now, what does heat do? Its effects.
Well, the most obvious effect is it changes temperature, right? Add heat, things generally get hotter. Remove heat, they get colder.
Makes sense.
But it does more. It causes things to expand, thermal expansion.
We mentioned that with thermometers at bridges.
Materials change size, usually getting bigger when heated. It can also cause a change of state.
Solid, liquid, gas.
Exactly. Melting, freezing, boiling. Those are all caused by adding or removing heat. Heat can also speed up chemical reactions.
Like cooking food. Heat makes the chemical changes happen faster.
Good example.
Yeah.
And finally, enough heat can kill living organisms, like bacteria during pasteurization or sterilization.
Okay, let's unpack a couple of those. Change in temperature depends on how much heat, what the stuff is made of, and how much stuff there is, right?
Correct. Absorbing heat raises the temperature. Losing heat lowers it. How much depends on the substance's mass and its specific heat capacity, how much energy it takes to raise its temperature.
And thermal expansion, things getting bigger when hot, smaller when cold, that seems pretty universal.
Mostly, yeah. Most substances expand on heating, contract on cooling. Water's a bit weird near freezing, but generally that's the rule. Engineers constantly have to account for it.
Okay, then the big one. Change of state, solid to liquid, liquid to gas.
Let's break them down. Melting, or fusion, is solid to liquid, like ice turning into water. This happens at a specific constant temperature called the melting point. For ice, that's 0 degrees C.
And you have to keep adding heat to make it melt, even though the temperature stays at 0 degrees C.
Exactly. The energy goes into breaking the bonds holding the solid structure together, not raising the temperature. The sources mentioned an activity showing this, the temperature stays flat during melting.
Okay. Then freezing is the opposite. Liquid to solid.
Yep. Water turning back into ice happens at the freezing point, which for pure substances is the same as the melting point. So 0 degrees C again for water. Heat has to be removed for freezing to happen.
Got it. Melting and freezing points are the same temp. What about liquid to gas?
That's vaporization or boiling. Water turning into steam, for example. Happens at a constant temperature called the boiling point, 100 degrees C for water at standard pressure. Again, you need to continuously add heat to make it boil.
And the reverse, gas to liquid.
Condensation. Steam turning back into water droplets, say on a cold surface. This also happens at a constant temperature, the condensation point, which is the same as the boiling point, 100 degrees C for water. Heat is released during condensation.
Boiling and condensation points are the same too.
Okay.
And then there was sublimation.
Ah, yeah, the weird one. That's when a solid turns directly into a gas, skipping the liquid phase entirely.
Like dry ice. Solid carbon dioxide just vanishes into gas.
Perfect example. Mothballs. Naphthalene do it too, so does iodine. Just needs the right conditions. And the reverse, gas straight to solid, is sometimes called deposition or solidification.
Wow. So heat drives all these transformations between states.
It's the energy that either breaks the bonds holding particles together, melting, boiling, sublimation, or allows them to form freezing, condensation, deposition.
Okay, Hugh. We've really covered a lot of ground here. Started with just feeling hot and cold.
And ended up seeing heat as this fundamental energy transfer driven by temperature differences.
We looked at the big sources, fire, the sun, electricity, and how they've shaped our world and technology.
We clarified that temperature isn't heat itself, but a measure of that internal particle energy, that jiggle.
Right. And how we measure it with different scales, Celsius, Fahrenheit, Kelvin, and the thermometers that rely on expansion.
Don't forget the conversions. C5, F32.9, always useful.
Definitely. And finally, all the things heat does, changing temperature, making things expand.
And crucially, changing the state of matter, melting, boiling, freezing, condensing, even sublimating. These effects are everywhere.
It really ties together so much, from tiny particles moving to huge weather systems and the engines in our cars.
It's fundamental physics playing out all around us all the time.
So here's a final thought to leave you with. Just take a moment and think about how much the principles we've talked about, heat moving, things expanding, how much they shape your everyday tech.
Yeah, it's kind of amazing when you stop to consider it.
Your car engine, the heating or cooling in your house, even just making a cup of tea or coffee. It all relies on this physics of heat. What other, maybe less obvious things in your life depend deeply on these ideas?
It's a really interesting question to ponder. How much of our engineered world relies on managing heat?
Exactly. Something to think about. Thanks for taking this deep dive with us.